Hello and welcome to another segment of Geology 1 Processes and Products Lab DVD. Today we're going to talk about topographic maps. When geologists are out in the field, they need a convenient way to describe their precise location to other scientists and other geologists. If a geologist runs into a landform that he or she describes, he or she needs to give the location that another scientist, another geologist, can end up at the same precise location. So how do we do that? How do we describe where on the Earth we are? There are a couple of different methods, and we'll be going over some of them in this segment. The first, the one that we're mostly introduced in early on in our high school career, is latitude and longitude. Latitude lines run from east to west, and they're used to locate how north or south a location is. Well, that sounds kind of strange, except if you realize that if a latitude line runs across a surface, we're then looking at how far above or below the equator an object is. The equator, of course, is the imaginary line that runs around the center of the Earth. Longitude lines, on the other hand, are those north-south lines that are used to measure how east or west a location is. Now, since we don't have an imaginary center of the Earth in that north-south direction, the standard has always been the prime meridian. That's given an assigned number of 0 degrees longitude, and it runs through Greenwich, England. Let's look at the globe. Here we see the equator, and here is the prime meridian. You can see that this is labeled as 0. Coordinates of latitude above and below the equator are assigned numbers: 20 degrees above, 20 degrees below the equator, north, south. The prime meridian also uses 20 degrees to the west or east of the prime meridian. So, where exactly would we put point C? Well, let's look at its location from the equator. If we look at the location from the equator, we see that we are 20 degrees south. If we look at the location from the prime meridian, we see that we are 40 degrees east. So, sure enough, you would write that as 20S and 40E, south and east. Once we have a map with latitude and longitude, how do we know how big something is on that map? We can always draw a map in various scales. We can have big maps with lots of information, or big maps with very little information where the distances are represented in a much larger fashion. We need to look at the bar scale. Maps have a bar scale which gives a corresponding amount of land distance to the distance on the map. A ratio scale is usually given as well, and this gives the ratio of the map distance to the land distance. Let me show you on one of the topo maps you may encounter in a lab. Now, we know it's very fine scale, but if you look up here, you will see that there is, in fact, a bar scale, and it tells us our distance, first of all, in kilometers. This is kilometers up here, and this is in miles. And at the bottom, we also see a nice ratio scale. So, the map scale will tell you the distance that corresponds to the Earth and the map. The public land system in the United States uses principal meridians and baselines. The principal meridians, north-south lines, and the baselines, east-to-west lines, to divide up land. Now, grids of 6 miles by 6 miles are created, and they're labeled. We go ahead and label from the north and south squares, either north or south of our baseline, and I'll show you that diagram in just a minute. But north or south of our baseline we refer to as townships, and they are abbreviated with the capital letter T. The east and west squares, again, we are going from a principal meridian that will run from north and south, and the principal meridian, we will then go ahead and locate our position either west or east of that principal meridian. These are called ranges, and they are symbolized by the capital letter R. Now, occasionally we don't refer to townships and ranges, we just sort of shorten that to townships. So if you run into the township location or the township section, realize that it also has a range coordinate as well, but we commonly just refer to this as townships. Here we go. Now if you look up at the top, you will see up here, here's a principal meridian that runs from the north and the south. Here is a baseline. Now, from the principal meridian, if you look carefully, you will see that we have range 1, range 2, range 3, and this is to the west. We also have range 1, range 2, and range 3 to the east. Now, from the baseline, we are looking either from the north or the south. This would be Township 1 from the baseline and Township 1 from the baseline in the southerly direction. So, if we were looking at this, where would we place this one little section, this township? We would go ahead and count over from our principal meridian, 1, 2. So this would be range 2W. We would also place it from our baseline and count 1 south, so that would be Township 1 south. So this would have a location, this square, 6 miles by 6 miles, would have a location of T1S and a range of R2W. Now, that township of 6 square miles can be further subdivided to make locations even smaller, a little bit easier to find. Each township can be divided into 36 smaller squares and numbered from 1 to 36. It starts in the upper right and sort of snakes around in numbers, ending up at the lower right, and I'll show you that on the next slide. And each of these 1 mile square sections can be further subdivided into quadrants. Let's see how that works. Okay, remember this? This is our T1S or 2W or Township 1 South, Range 2 West, and we're going to blow this up 6 miles by 6 miles, and then we're going to divide this into 36 equal 1 square mile units and number them accordingly. 1, 2, 3, 4, 5, 6, 7, 8, 9, and continue on numbering until we reach our section 36. Now, within each of these square miles, if this is section 11, we can take this section, let's blow it up, and we can further subdivide into quarters. We have a northeast, a northwest, a southwest, and a southeast. Look at this southeast quadrant. See how it's been further subdivided? Again, into northeast, northwest, southwest, and southeast. And we can continue to further subdivide to get closer and closer to the exact location that we want to convey. So, there is a point Q. It's located right here. Where would we say point Q is located? If we have to describe this point, maybe it's a house, where would we say this house at point Q is located? Well, don't forget we have to go back to the original system. We do have to go back to the township and range. And like we noted before, we are in Township 1 South and Range 2 West. We are also within Township 1 South and Range 2 West in Section 11. So far, we would write Section 11, T1S, and R2W. But we can get a lot closer to point Q. Let's blow up Section 11 here. Note that we now have little quadrants. This would represent the southwest quadrant. Now we can say that we have point Q in the quarter of the southeast quadrant of Section 11 of Township 1 South and Range 2 West. Okay, we can actually get a little closer though to describing where point Q is actually located. Notice that even though we are in the southeast quadrant of section 11, we can further subdivide that southeast quadrant into quadrants as well. We can have northeast, northwest, southwest, and southeast. At that point, we can say that Q is located in the one quarter of the northwest. See, we are now in the northwest of the 1/4 of the southeast. Can we get even a little closer? Well, I think we can. I think we can take that northwest quadrant and divide it again. And if we do that with imaginary lines, we can see that Q is still located in that northwest quadrant. So, where is our point Q located? In the northwest quadrant of the northwest quadrant of the southeast quadrant of section 11 of township 1 south and range 2 west. Now remember, in the public land system, we still are looking at 1 mile squared as far as area covered. And farmers commonly deal in acreage. In each square mile, we have 640 acres. Let's suppose you wanted to purchase just 1/4 of the northwest section of section 11. So if we have section 11, let's imagine section 11, we divide it into quadrants. You want to purchase that northwest quadrant. How many acres are you going to be buying? Remember, when we divide into quadrants, we're dividing into fourths, or 0.25, so we simply multiply 0.25 times the fact that we have 640 acres per square mile. You will be purchasing 160 acres. Let's hope you get a good deal. The GPS, or Global Positioning System, is used a lot more commonly now. There are 28 navigational communication satellites within 12-hour orbits around the Earth. The good news is that it's a free system. And the handheld GPS units have come down in price considerably, where you can get, for just around $100 or slightly more, a pretty good unit. Of course, you can spend a lot more than that if you choose. Now, the receivers must process a minimum of 4 signals to triangulate the position. Another system that's used is the Transverse Mercator System, the Universal Transverse Mercator System, or the UTM system. This is based on a rectangular grid, and it's based in the SSI, or metric unit system. There are 60 north-south zones. Let me show you how that works. Here we go. You can see a flat Mercator projection of the world, and you see that we're starting at 0, 1 in this corner, and we're moving all the way through 60 here. We're interested in North America, so let's blow up this portion of the map and look at the system. Note that zones 10, 11, 12, 13, all the way here through zone 19 cover the continental U.S. Now, what's also nice about this is that we also have the corresponding longitudes for the UTM system located at the top of the map. Now, fortunately, the Universal Transverse Mercator System coordinates are usually labeled on maps. And here in this diagram, I've pasted them in because the original topo map somehow was printed without them. But if we want to find the location of point X using the Universal Transverse Mercator coordinates, how would we do that? Well, note that the way that the numbers are abbreviated is for convenience because we're dealing in thousands of meters. So, where is point X? Point X would have a northern coordinate, here we go on this side, of 3,785,000 meters north of the equator. This is the number that would be given over on the right-hand margin of the map. Now, what about the eastern coordinate? Again, you look either at the top of the map or the bottom. Here we would have an eastern coordinate of 445,000 meters east. Simply look for your UTM coordinates on the map and estimate accordingly. Compass bearings. Kind of old-fashioned in some sense, but still very, very useful. We can utilize either quadrants, the north, south, east, west traditional, or we can use azimuth bearings. Well, let's look at this diagram. If we want to go from point A to B using the old-fashioned compass quadrant readings with the north, south, and then of course east and west, so northeast, southwest, southeast, southwest, and northwest system, how would we describe A to B? Well, we would use a protractor and try to find that angle from a vertical line right through that point A, and then measure the angle from that upright to point B. And if we look carefully, we can see that's about 42 degrees. So this would be north 42 degrees east. The compass direction is north 42 degrees east toward point B from point A. Now, what if we use the azimuth bearings? Well, in this case, we divide up our compass into 360 degrees. Now, because we are still in that northeast quadrant of our compass, we are still at 42 degrees. What if, however, we wanted to go from point B to point A? Well, that would be just a little bit different. 42 degrees from point A to point B, but if we imagine moving this compass over in this direction and going from point B to point A, we would read this bearing. Note that we have 180 degrees here, so we would look at 190, 200, 210, 220, about 222 for our azimuth bearing. Topographic maps are two-dimensional representations of a three-dimensional surface. We use contour lines to show the elevation that we can't show on a flat piece of paper. Contour lines connect all the points of equal elevation along the map. We don't label the elevations of all the contours, however. We use index contours. These are the heavier contour lines. They're printed in a darker font size, and they have the elevations printed on them. Now, the distance between one contour line and another contour line is known as the contour interval. Many times you will see the contour interval actually printed in the map key. Let's take a look. Here we have a three-dimensional island emerging from the ocean. How would we represent the changes in elevation on a flat piece of paper? The way we do that is in a topographic map through contour lines. Note at sea level we have 0 degrees elevation, and we essentially outline that location at the base of this island as a 0 contour line. Then if we would contour at 50, let's see, we are working in feet, 50 feet above sea level. We would take 50 feet all around this island and map it accordingly. And then finally, if we're in a 50-foot contour interval, we would do it at 100 feet also. That would translate to this line up here. And we didn't make it to 150 feet, or we would also have a contour for 150 feet. There are some rules for contour lines. Contour lines have to always close on an irregular circle. Now remember, however, that a topographic map may not show the entire mountain or the entire basin or the entire landform. So you may have lines that go off of the page and don't close. That's okay. However, you can't have contour lines that cross, because after all, one spot on the earth can't be at two different elevations. If it's 50 feet, it can also be 100 feet as well. Now, contour lines can come together and merge if we have a cliff or a vertical wall, because a flat surface, a vertical surface, represents several different heights above the surface of the earth. The closer together that contour lines are, the steeper the slope. Widespread contour lines indicate flat, low slope land, but when you get them very close together, you're looking at steeper terrain. Let's take a look. If you look at this map, you can see, number one, that we have some closely spaced contour lines right about here. And this would indicate that it's fairly steep in this area. There's a corresponding artist's rendition of what the land actually looks like up here. And you can see that there is a fairly steep slope up on that little ridge. As the contour lines get farther and farther apart, we're getting into flatter and flatter land. Other rules for contour lines. If you have a concentric contour, as we move up, we are looking at a hill. However, we also can have concentric depressions, and the way we represent those is through the use of hachure lines that show in the direction that the land is sloping down. I'll show you that in just a minute. Now remember, rivers have channels and they cut deeper into the land that they run through. So therefore, when you find a river, you'll see that the contour lines make a V, and the V always points up the slope. Let's look at that on this map. Okay, here we have some little concentric spots, and these would be slight hills actually on a ridge. But look at this. See how we have the nice concentric contour lines coming up. Here we have a hill. At the top of the hill, oh, maybe we have a volcano because it looks like we have a depression, a crater. Look at the hachure lines moving toward the inside of the crater. Now, here is our river. Notice the tributaries are almost V'ing into the river with the V pointing down, but that's not what we're looking at. We're looking at these brown contour lines, and note that these V's point uphill or upslope. It's a good rule to know when you're trying to interpret a topographic map. The gradient is the steepness of a slope. Let's go ahead and use that map that we were just looking at, and we're going to calculate the gradient, or the change in elevation over the distance from the river to that rim of the crater. Okay, here we go. Now, let's go ahead and put some points so we know where we are. Let's go from the rim of the crater here. We're not going to where we're actually moving into the depression. We're going to stick right here. And let's go back to the river. Okay. Put a flat edge connecting the 2 points. So we're going to be here at this X, and this is where we'll end up. Now, what's the distance? We have to go down to our faithful map key. And 1 inch is about 1 mile. If I line up, there's 1 mile. Line up again. There's 2 miles. And unfortunately, this doesn't give me very much to work with, but if that would be 3 miles, and that would be, we're looking at about 2¼ miles. Okay? So, the distance from the river to the crater is about 2.25 miles. Can we calculate the gradient? Well, not quite, because we know the distance from the river to the top of the crater, but we don't know how much change we've seen in elevation. Let's go back to the map. And here we'll see that we are at 0 degrees elevation for the contour line. And here at the lip of the crater, we are at 200. Now, it doesn't tell us 200 what? 200 feet, 200 meters. We come back to the map key at the bottom, and it tells us our contour interval is in 20 feet. So we know that this represents 200 feet. Now we have the distance from the river to the crater as 2.25 miles and the vertical relief at 200 feet. So, what's the gradient? The gradient, again, is the relief over the distance. So if we divide 200 feet by 2.25 miles, we come up with 88.9 feet per mile. Now, of course, if you punch that in, you'll get the answer of 88.8888. But remember, we're looking at scientific notation. We're looking at the digits. So therefore, when we have 200 and we have 2.25, we have basically 3 significant figures here and 3 significant figures here. our answer should also be in 3 significant figures. How do we construct a topographic profile? You're going to be asked to do that. You have to use a straight edge, similar to what I just did with the gradient, and you need to locate each of the contour lines that hit along 2 points. So you decide where you're going to construct your topographic profile. You can choose any 2 points, or 2 points can be chosen for you, and you draw a straight line between point 1 and point 2. And then when you put your straight edge against that line, you mark any contour lines or any special features, such as a river, which may be crossing between those 2 points. Vertical measurements are often exaggerated to show the relief of an area. If we plot the vertical in the same scale as we do the distance or the geographical locations, the vertical relief usually isn't great enough for us to see differences. For example, this actually is from a textbook in the 1939, almost to 1940. But this diagram comes from 1830, a geologist by the name of Henry Della Beach. And he wanted all geologists to use the regular scale, which is this. This would show the exact relief compared to the distance covered. He showed the dangers of what could happen if you were using an exaggerated scale. Here is a regular scale, again, no vertical relief. Here is another with no vertical relief. But if you show vertical relief, Della Beach believed that this wasn't exactly a great idea, that you exaggerate features and the geologist in the field might not be able to interpret as correctly as he or she should. Well, that idea really didn't take hold, and we do use vertical relief now. Okay, let's go through step 1 again. If 2 points are given for you, here's A and A prime. First off, we connect the 2 points with a straight line. Then we put a piece of paper, a straight edge. You don't want to just tear something out of the notebook. You want to make sure you have something about as heavy as cardstock so that you don't get too many bends and folds. Mark where A starts and where A prime ends. And any contour line that hits the line, you mark on the piece of paper and mark what it is. 80, 100, 100. 80 again. Oops, we have a stream here. Here's another 80. How do you know which elevations the contour lines are? Well, you figure that out either from the index contours, which are labeled, and if you're moving downhill from 100 down would be 80 if you have a 20 contour interval. Now, are we working in feet? Are we working in meters? Let's go back. Okay, looking at this map, we should see a contour interval. Unfortunately, in our little diagram, it's missing. However, the contour interval is in feet, and you would be seeing that somewhere on the original map. So we are in feet. Now, what do we do with that information after we have it located along the straight edge piece of paper? We then take a graph, and we can choose what our vertical exaggeration is going to be. In this case, we have some graph paper, and we're measuring the elevation off in feet, 40, 60. We're using a 20-foot contour, 80, 100, 120, 140. And we take that straight edge with all of our little contour markings on it. Remember where the stream passed? Well, we take the elevations. Here we see 80, so we plot A, then 80 must cross the 80 contour, 100, go up to 100 feet. We hit 100 again. There's another 100. Down to 80. The stream, we know from our map the stream is down a little bit lower. Then 80. Then 100, and we continue on in this fashion, 120, 140. When we actually draw our line, we're not going to play dot to dot. We're not going to go A, dot, 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 because we're not going to have a mesa here. If you think there is a mesa, of course, you would draw flat at the top, but we know from our map that it was a rolling topography, a rolling landscape. So you do your best to kind of connect in a fairly free form. Connect the dots, but try not to make the connections very abrupt. Okay, so what is the, we have the vertical elevation that we need to figure out. We know the horizontal scale because that's going to be on the map scale. And if we go back to the map scale, we'll see that that's 1 inch would be equal to 24,000 inches in real life. That's printed on the map. But what about our vertical scale? What about the vertical elevation? Okay, here is our original A to A prime, and here is the ratio 1 to 24,000 printed on the map. This gives us our horizontal ratio. What about that vertical? Well, the vertical scale is determined by measuring the distance that is represented on the map, the changes in elevation, and how we plotted that on the vertical scale that we just constructed with our straight edge. Okay? For example, if we have 1 inch would be equal to 120 feet on our profile, then we would say that 1 inch on our profile, our vertical profile, is equal to 120 feet on the Earth's surface times, we need to get this in inches. Remember, we're working in inches, so we have to compare inch to inch, just as we did here. 1 inch is 24,000 inches on the Earth. So 120 feet times 12 inches per foot, remember feet cancel out, and we're left with 1,440 inches. Our vertical scale is equal to 1 to 1,440. So that means that for every 1 inch that we move up on our vertical profile, we would have to move 1,440 feet on, 1,440 inches on the Earth. 1 inch equals to 1,440 inches on the Earth. There's a difference here. The horizontal scale is 1 inch to 24,000 inches, and the vertical scale is 1 inch to 1,440. So we do have vertical exaggeration, and we will calculate that next. Let's look at this for just a minute because I do want to make sure that you understand how we figured out, if we go back to this slide, that 1 inch would be equal to 120 feet. Remember, you could choose your own scale to plot your vertical topographic profile. Now, you may do this through trial and error and at some point get very, very flat profiles and you realize you need to exaggerate it a little more. Or you may end up with something hugely exaggerated and you realize it's not very useful. Therefore, sometimes it's a little bit of a trial and error phase depending on what area of the country you're trying to represent. However, this is the scale that we used in our example, so if we would take a ruler, for example, and go from this 80-foot contour interval to, let's see, we want to go to 1, 2, 3, 4, 5. Let's say the 160 contour interval, we would see that we're passing 80 feet in a given distance. Okay? Now, whoops, wrong way. Sorry about that. 1 inch is equal to 120 feet on this scale. I know it doesn't look like it here because I do have it blown up so that you can see it. So if we went from 80 to 200, which is way up here, this would be equal to 1 inch, 120 feet. You need to measure your contour lines and figure out between contour lines how much distance is represented. So, let's go back to our vertical elevation. The horizontal scale, 1 inch, is 24,000 inches. Our vertical scale, 1 inch, is 1,440 inches. Therefore, our vertical exaggeration is figured out by dividing our horizontal scale by our vertical scale, or 24,000 is divided by 1,440. And we get a vertical exaggeration of 16.7. That means that our vertical scale has been exaggerated 16.7 times in relation to our horizontal scale. And again, we do that because it makes it a little bit easier for us to see the topographic relief. This will conclude our section on topographic maps. Now, we realize that when students first encounter topographic maps, it can be a somewhat difficult topic to get a grasp on, and we encourage your questions. So please feel free to email your instructor, and he or she will be happy to help you. We do know that some of the diagrams we've shown today with the PowerPoint slides have been very, very simplified, and some of the maps you will be encountering will be much more detailed. Don't worry, we're here to help, and we'll be happy to answer all of your questions. Thank you very much for joining me today. Have a good day.